Okay, so good morning to all of you. So we'll start with today's session. So yesterday we have solved this problem, and we have also solved one more problem for multiple regression. And the output was something like this. So I'll go back to the output once again. So we have received something like this. One was regression statistics table, second was ANOVA table, and then third was coefficient table. And then we have discussed the meaning of R square and the meaning of adjusted R square also. And then we have seen that how these coefficients are useful to create the data model or the regression equation. Now we will see what is the meaning of multiple R, and then what is the meaning of standard error, and then we will solve one problem today of multiple regression, for which I have shared the Excel file with you about the blood pressure values, and then we will start with hypothesis testing. So basically multiple R is nothing but your correlation coefficient. So what we have calculated using equal to CORREL formula, correlation formula, that is the same value. So it is just showing me the what is the correlation coefficient between X and Y. So that is multiple R. R square we have discussed, adjusted R square we have discussed, and now we will discuss standard error also. So in case of R square, what is R square? In case of this example, if it is 0.17, that means only 17% of variance in Y is explained by X. That is what we have discussed. So X is not a good predictor of Y. In other words, what we can say is only 17% of data fits into the model. Whatever model we have defined using these coefficients, Y equal to something plus something, that model, if I implement this model, if I want to use this model, only 70% of data is fitting into the model. So this is not a good model, or X is not a good predictor of Y. Adjusted R square and adjusted R square are close enough, means not much chance of adding or removing any predictors or any independent variables. So they should be close enough. And next is standard error. What is standard error? It represents the average distance that the observed values fall from the regression line. So it tells you, it is basically the deviation. The maximum the deviation, maximum will be the larger will be the standard error value. So it tells you the how strong the regression model is on average using the units of response variable. So basically standard error tells you the accuracy of the model. Standard error tells you the accuracy of the model. So R square tells you how many data points are getting included into your model. What is the strength of your model? What is the goodness of your model? Adjusted R square tells you how good your predictors are. Do you want to add or remove some predictors? And standard error tells you the accuracy of the model, how your model is accurate. Larger the standard error value, that means your model is not that accurate, or you should not include those values which are beyond standard error. Generally, a thumb rule in analysis is you should consider adding those observations which are in the range of 2 into standard error. Which are into 2 into standard error. Just like in case of standard deviation, we say 3 standard deviation is a normal. Like one standard deviation consists of 65%, then one standard deviation 68%, 2 standard deviation 95%, and 3 standard deviation consists of 99% of the data points. And based on that, we calculate the outliers. Similarly, in case of accuracy of data, goodness of model, you should consider all those data points which are in the range of 2 into standard error. The deviations which are in the range of 2 into standard error. So we'll use all these things and we will do a detailed analysis for the blood pressure data. So this was the first problem, correct? Now in this problem, if I calculate the correlation using the formula correlation between X and Y. So I'll provide all the values of X, comma, all the values of Y. So what I'm getting is the correlation coefficient, that is the same value. Multiple R gives the correlation coefficient, nothing else. It is just the unsigned value. It just shows the strongness of relationship between X and Y. So this is just this value is just telling me that they are strongly correlated. X and Y are strongly correlated, but that doesn't mean that what we have discussed is correlation is different and causation is different. In regression, we are trying to establish the causation also. In correlation, that is only based on numbers. So only based on numbers, what R is telling me, multiple R is telling me that they are strongly correlated to each other. But then R square is telling me that there is some causal relationship also. That's why 95% of data points are fitting into the model. Y can be explained up to 95% using X values. And then adjusted R square is telling me that my model is very good. I don't have to worry about my predictors. So my X is a good predictor of Y. And then standard error is also very less. 4.30 is almost very less. So even if I go for two standard deviations, or sorry, two standard errors, that will go to a maximum up to 9 or 10. So that much of standard error is also acceptable. So because now we have only one independent variable and one dependent variable, actually these values doesn't matter that much. My values will come very close to each other. But that is the meaning of multiple R. It is just giving me the correlation coefficient. Now look at the second problem, education and earnings. The R which we have calculated, correlation formula, that R is 0.422, and what we are getting as multiple R is also 0.422. So again, multiple R only gives me the correlation coefficient. So this is the Excel file which I have shared with all of you. The first sheet consists of the actual data, the data which has been received with the columns like age, years, weight, height, chin, forearm, calf, pulse, systole and diastole. So we have these two variables which we are actually trying to create models for. First is a systolic blood pressure, which is the upper value of the blood pressure, higher blood pressure. And second is diastolic blood pressure, which is the lower value or low blood pressure value. And we are trying to create a data model using the variables like age, years, weight, height, chin, forearm, calf, and pulse. We don't know whether all these variables are required in my data model or some of the variables I should exclude. So I need to create a data model out of it, so that for any person, if I know all these variables, if I know age, if I know weight and height, and if I can predict the high blood pressure and low blood pressure for that person, then that person don't have to come to my clinic every time. Maybe something like that. So I'm trying to create a data model for high blood pressure and low blood pressure. Now in third sheet, I have given the meaning also. What is the meaning of systolic blood pressure? What is the meaning of X1? That is age. X2 is years in urban area. So how many years that person has been living in urban area? Because as we know, we have different habits and different kind of culture in urban area and rural area, which has an impact on all our body, and that includes blood pressure also. So we are considering that as one of the factors. Then it is given in the problem statement itself that you have to calculate X3 manually using formula X2 upon X1, that is years in urban area divided by age. So fraction of your life in urban area. So if your age is suppose 40 years, and out of 40 years, if you have been living in urban area for 20 years, that means 50% of your life is in urban area. So that fraction of life I am calculating, and then weight, height, chin, forearms, calf, and then resting pulse rate, that is pulse rate, normal pulse rate. So these are my variables, or we can say these are my independent variables, X1 to X9. And right now we are going to consider this systolic blood pressure as my first Y, that is dependent variable. So we'll create a different model for systolic blood pressure, and then we'll try to create a different model for diastolic blood pressure. So first thing is, first we have to calculate that X3. So that also I have done. So you can find out in second sheet. I have given that calculation for you, B3 upon A3. We are all B values divided by A values. So that column has been already calculated and the data is already present. Now for this data, now we have to create a regression model. So for regression model, first of all, by default, as we have discussed, we'll go to data and data analysis, and we'll select the regression option. And first iteration, we'll consider all the independent variables as part of the data model. So I'll consider all the independent variables as part of the data model from X1 to X9. Sorry, that is X. Okay. And Y. As Y, I'll consider only systolic blood pressure. So I'll consider this YS as my systolic blood pressure. So I have given Y values, I have given the X values. Labels, yes, I have labels in my first row. Let the confidence level be 95%. After some time, we'll discuss what is the confidence level. Output range, yes, I want to display output from this cell, and then I want to display residuals. Still, I'll go ahead with residuals for some analysis, and then I'll click on OK. So I'm getting this kind of output. So this multiple R tells me that there is a strong correlation between all the independent variables and this dependent variable. So relationship is strong. So at least we can say that we are moving into right direction. R square value is 0.66. That means up to 66% of data is fitting into my model. So I may say that this is close to acceptable value. I'll try if I find some other model with some other variables, combination of other variables. If I can go up to 0.70, that will be better for me. But still 0.66 is close to acceptable value. Adjusted R square tells me 0.56, which is, I can say, not that close to R square because the difference is almost 10%. But still, because only we have only one model right now, so we have to accept this model as it is. Standard error is 8. So that is also on lesser side. That is okay. We don't have any problem with standard error also. ANOVA we'll discuss in tomorrow's session. These are the coefficients in coefficient table using which you can write the equation for the data model. Ys is equal to all the variables into their coefficients and plus last intercept, which is a constant. So that also you can do. Now look at the residuals. Looking at the residuals for all 54 values, these are the deviations from my expected values. Now, in terms of deviations, I have to find out whether if I have taken any outliers, and if I remove those outliers, then can I get a better model? So for that purpose, we will go to that step of iterative regression models. But first of all, my request to you is you take 5 minutes, and in next 5 minutes, you try out your own combinations based on your own logic.
Sir, I have taken the age, year, friction, weight, height, and systole.
Okay. So what is the R square value?
It is, wait a minute. It's 0.49.
So it is lesser than what we are getting right now.
Yes, sir.
Okay, so 0.49 is the R square value for all the variables from x1 to x5.
Year, weight, height.
Yes, x1 to x5.
Yes, sir.
Okay, and what is the adjusted R square?
0.36. That is
0.36. Even the difference between R square and adjusted R square is very also large. Okay, fine.
10%.
Okay, so we cannot accept this model. Next.
Yeah, when I have removed x6 and x7.
Okay.
Sorry, x7 and x8, that is forearm and calf, then I am getting the value as 0.64 R square.
x7 and x8, 0.67.
Yeah. 0.64.
64, okay. And what is the adjusted R square?
R square is 0.56.
0.56. And what is the error?
Error.
Standard error?
Yeah, 8.66.
8.66. Okay. So at least we can consider this model for discussion. So the R square value is 64.64. So not much difference between R square value of the complete model and this model. So that is okay. The adjusted R square difference, in this case it was almost 0.1. In this case it is 0.08. So even the difference is very less. And in case of standard error, it is almost constant, same rather. So we can say this is a better model or this is a better model. What is your suggestion?
The first one, sir. R square is 66%.
This one?
Yes, sir.
Okay. Anyone else? Which is a better model out of these three?
I think, sir, first one.
Yes.
First one is here.
Yes. So we'll go ahead with the first model. You can also go ahead with this third model also. That is, there is no problem as such. But the difference or the value of R square is not significantly different to go and select the third model. So I'll still go ahead with first model, better model, which includes all the variables. We don't know whether the cough and pulse may also have some effect or effect on the blood pressure. So because we are not from that domain, so we cannot just exclude the variables based on these numbers. If numbers are significantly different, then yes, we can exclude those variables. So right now I'll go ahead with the first model. Now what we'll do is, now I'll tell you some key methods which you will not get anywhere on any online site or anywhere. How to run the iterative regression models. Now this is the decision we have made that we'll go ahead with the first regression model. Fine. Now what is the standard error value? Standard error value is 8.6. And we have discussed that my 95% of data should be within 2 standard error. So if I go for 2 standard error, if 8.6 is 1 standard error, the 2 standard error value comes somewhere around 17. 17.2 or something. Now 17.2 is the complete 2 standard error region. But I don't have to consider the complete 2 standard error region, which is 17.2 distance, because R square is telling me only 66% of my data is fitting into the model. Only 66% of data is fitting into the model. So what I have to do is, even I have to take the 66% of my 2 standard errors. So say roughly 70%. So what is roughly 70% of my 2 standard errors? So 70% of 17 somewhere comes about 12. 70% of 17 somewhere comes about 12. So I can consider a distance or the deviation up to 12 as an acceptable deviation in my data model. So if 12 is the acceptable deviation in my data model, and if I go to residuals, I have to find all the residuals which are 12 or greater than 12 on both the sides, positive and negative. So I'm finding this observation is having deviation greater than 12, and this observation is having deviation greater than 12. All other remaining observations, yes, this model, this data point is also greater than 12. Remaining data points, I don't find any deviation which is 12 or greater than 12. Remaining all deviations are less than 12. So that is fine. So what this standard error and R square combination is telling me that these 3 data points can be outliers. So actually
so the first one is first one deviation 13.47.
Fine. Okay. Yes. First one is also there.
Yes.
So these 4 data points may be outliers. These 4 data points may be outliers. So number of observations are like 40, around 40 observations I have. Out of 40 observations, I can have 4 observations which can be outliers. Rather, I'll frame this question in a different way. That can I exclude 4 observations from my 40 observations? Now 4 out of 40 is almost like 1%. So can I exclude 1% of my data? Can I exclude 1% of my data? And if it is acceptable as per your company policy for whom you are doing the analysis, then you can exclude, you can go on and exclude these 4 data points. Now data point numbers are given to you. Observation number 1, 8, 10 and 11. Now have you understood this concept basically? How we have arrived and how we have found out this 4 values?
Will you please explain one more time,
Yes,
sir?
yes. So basically we are now trying to combine R square and standard error. Now standard error tells me that 8.6 is the value of standard error, and we have discussed the rule of standard error that my 95% of data deviation wise should be inside 2 standard errors. So that 2 standard error, if I consider 8.6 as 1 standard error, 2 standard error comes to be somewhere around 17.2. So if 17 is my 2 standard error, that is the accepted deviation, considering my good data model, that 100% data fits into the model, my 2 standard error is 17. The deviation, accepted deviation is 17. But now all what R square is telling me that out of 100, only 66% of data is fitting into the model. So if only 66% of data is fitting into the model, even I have to consider only 66 to 70% of the standard error, 2 standard error. So 2 standard error is 17. So I have to find 70% of 17, 17.2, which somewhere comes around 12 point something. So 12 point something is the accepted deviation as per the data model which I am creating based on R value of 0.66. So if 12 or above 12 deviations are there in my data model, then they can be outliers. I am not sure. I'm just trying to find out, are they outliers? So now we are going to find out that also. And in the process, now we are going to create a stronger model also. So I am going to consider all the deviations which are 12 or greater than 12. So I find that these 4 observations are having deviations which are greater than 12. So now what I want you to do is, you take 2 minutes, exclude observation number 1. Now this is my observation number 1. So you have to exclude this row. Now we are not excluding the columns. Now we are going to exclude the rows. And now we are going to exclude 4 rows. Observation number 1, that is row number 1. Row number 8, that is observation number 8, 10 and 11. So now you exclude these 4 observations from this table and rerun the regression, and now tell me the R square and adjusted R square value and standard error value. 70.
7.
Okay, and what is the adjusted R square?
0.59.
0.59. Okay, and what is the error?
It is 7.03.
7.03. Okay. So now if I compare these numbers with these numbers, I think my second model is a good model or a better model than the first model. That means the 4 values which I have excluded, I can consider them as outliers. If my R square is improving and if my standard error is also decreasing, and adjusted R square difference is almost same, is not that much of difference. This is 0.1, this is 0.11. So even that much of difference is the same difference is there in second model also. But my R square now my data model is trying to include 70% of data points. So both the data models are good in a way. So if you are allowed to exclude 4 variables, 4 observations, then you can go ahead and you can select this data model. And if you're not allowed to exclude the 4 observations, then you can surely go ahead and you can take the original model. So in comparison with both the models are good. Both the models are giving good R square value. 66% and 70% doesn't make any difference. But yes, if you are ready to exclude some of the observations, this is a better model always. 0.70 is always better than 0.66. So that's it about the regression and iterative regression. Now, because we are handling only 40 around values, we have gone into first iteration. Consider if you are handling 4,000 or 40,000 values, you may have to go ahead and do at least 3 to 4 iterations of regression model. And in reality, generally you have thousands of observations and at least 10 to 15 columns as 10 to 15 variables. So with that combination, generally the regression analysis goes for at least it's a task of couple of days. You have to consider all the combinations of the variables, predictors, then you have to consider all the observations, which observation you can exclude, finding out the outliers, trying to get a better model in terms of R square and standard error. So that's why regression analysis is a complex task, and generally with real data, you may want to take at least couple of days to do the complete regression analysis. So now I request you to open that hypothesis testing case study and read that case study. It's a 1-page case study, simple case study. Just take 2 minutes and then we'll start with hypothesis testing.
Yes, sir.
So the last statement is very important in this case study, that in hypothesis testing, we begin by making a tentative assumption about the population parameter, and this tentative assumption is called as null hypothesis, and it is denoted by H0, or it is also called as H0. We then define another hypothesis called as alternate hypothesis, which is the opposite of what is stated in the null hypothesis, and this is denoted by HA, or alternate hypothesis, or even you can define it as H1, denote it as H1. So H0 and H1, or H0 and H1, or HO and HA, whatever notation you want to use. So basically on day 1 itself, when we discuss why we need statistics, in that case, we assumed that my population average salary is 80,000, around 80,000. And then we have checked whether my assumption is correct or not. So always when we start doing any kind of analysis, we need to have some basic assumption about my analysis, and then we go ahead and check whether my assumption is correct or not, how my actual value is deviating from my assumption. If the deviation is significantly large, then my assumption is wrong. If the deviation is significantly small, then my assumption is correct. So that is how we do check our assumptions. And the process of checking this assumption is nothing but hypothesis testing. So whatever assumption I will write, whatever is the statement I want to check, that becomes my hypothesis statement. And then how to, whether to accept or reject that statement, that process becomes hypothesis testing. So first, whenever I get any problem, the first step is I need to define my hypothesis statement. And the second step is I need to test whether my hypothesis is correct or wrong, whether I can accept or reject my hypothesis. So in this case, for this problem, if you have seen, based on the available data, whatever data is given in the case study, my null hypothesis H0, if I want to define, I can define it as P is less than or equal to 0.50. And exactly opposite of H0 is my alternate hypothesis, which is HA, which comes as P is greater than 0.50. But this is just to understand the meaning of hypothesis statement and H0 and H1. Now we'll write few hypothesis statements from actual problems, and we'll try to test those statements also. Hypothesis testing. Actually, this is a very vast topic. Whatever I have covered from day one, we are taking 2 hours per day session, and this is our 5th day. That means I'll be covering 10 hours by today's session, end of the today's session. But generally, this is a 40-hour course. So whatever I'm telling you in 2 hours, generally in a classroom with students in the class, we take 3 to 4 hours to explain the same concept. So I'm trying to give all the only important details which are required to be told about that concept in this course. So in case of hypothesis testing also, there are a lot of things which can be discussed. But what is the most important part in hypothesis testing is you should understand what kind of data you are handling. First thing is you should understand what kind of data you are handling. What is the meaning of this statement? The meaning of this statement is if you know the data completely, that means if you know the population parameters. In short, if you know the population parameters, if you know the population statistics. So when I say population statistics, from day one, we have discussed this, that only mean is not sufficient to understand the data. We need a combination of mean and standard deviation. So if you know mean and standard deviation of data, we have already solved the problems based on normal distribution, where I know mu and I know standard deviation. Just because of these 2 values, I can easily calculate Z value. I can go to Z table, I can calculate the distance, and I can come to the conclusion. So actually this branch of yes, that I know mu and sigma, we have already done. So this part of testing we have already done, but not in terms of hypothesis testing. We have just solved the problems based on the curve. So today we are going to look at the testing part also. But what if you don't know about the population parameters? That means you don't know the population statistics. That means you don't have the complete population with you. So you are dealing with samples. You are dealing with samples which are correct representative of the population. So in case of samples, we have to go for T distribution. We cannot use Z distribution. We have to go for T distribution. So if you're dealing with samples in case of T distribution, again, there can be 2 possible cases. That I have only 1 sample with me, or I can have 2 samples with me, or I can have more than 2 samples with me. There can be actually 3 cases. There is a 3rd case also, that I can have more than 2 samples also. So if I have only 1 sample with me, available with me from the population, I can go for 1 sample t-test. If I have 2 samples available from the population, then I can go for 2 sample t-test. And if I have more than 2 samples, with me, then I can go for F-test. So F-test is for more than 2 samples or multiple samples. So in case of 1 sample t-test, if you look at the formula is almost same as normal distribution. You look at this formula of Z, and that is same as formula for 1 sample t-test. X minus mu naught divided by S upon root n. Only the population symbols are getting replaced by the English alphabets, because we are now dealing with sample, nothing else. So 1 sample t-test is a very simple task. We'll solve some examples. but this is the formula for Z. In case of two sample t-test, now we'll come to the two sample t-test. In case of two sample t-test, again we have two possibilities. The first possibility is they are paired samples. When I say two samples, either, for example, if I'm teaching a course, like this course I'm teaching to this batch. So if I'm conducting one exam before starting the course about the understanding of the statistics, and if all of you have appeared for this exam, then I'll conduct the course, and then again I'll take the exam from for all of you to check whether you have understood statistics or not. So one test I have conducted before starting the course, and one test I have conducted after completing the course. So I am having two samples with me about the marks obtained by all of you. So I have these two data sets with me, two samples with me. But in case of these two samples, my the objects are remaining same. Same objects have appeared for first exam and same objects have appeared for second exam. In this kind of situations, I call them as paired samples. Same object has given me two different observations. So in this case, I can call them as paired samples. So this is a paired sample case, and for which we have a paired sample t-test. Now there can be a situation where I have two data sets, and the objects which from where I have taken all these data points are totally different from each other, are independent of each other. That I have conducted a test for class A and I have conducted a test for class B, for example. And then I am comparing the scores of class A and class B to know which class has done better. So in this case, the objects, the students of class A and the objects and the students of class B are totally different, independent of each other. There is no relationship between them. So in that case, I can go for independent sample t-test. In that case, I can go for independent sample t-test. Now, when I say independent sample t-test, again, in case of independent sample t-test, we have again two variations. When we say independent samples, just like what I have, what example I have given, that I have conducted one exam for class 1 and I have conducted one exam for class 2. Now, suppose we have 100 students in class 1. So it's a big class of 100 students. And my class 2 is a specialization class where I have only 8 students or 9 students. So can I compare a set of 100 numbers with a set of 8 numbers? So for this case, in case of independent samples, I have to look at the variance of class 1. What is the variance in class 1 and what is the variance in class 2? Even if the numbers are different, like class 1 has 100 numbers and class 2 has only 10 numbers, but if the variance is same, the dispersion, the spread of the data is in similar fashion in both the classes, I can go and compare both the classes. In that case, if the variance is same, I will go for this method. And if the variance is also different, the numbers are also different and the variance are also different. That means two classes are totally different from each other in terms of behavior. Then I have to use a different formula. So based on variance analysis, we have to choose correct method, appropriate method for execution. And the checking of variance is called as Leven's test. The checking of this variance is called as Leven's test. So Leven's test will tell us whether to go for which calculation formula in case of independent sample t-test. And please remember this point, which is very important, that whenever we deal with multiple samples, whenever we deal with two samples, independent samples, the most important part is analysis of variance. The most important part is analysis of variance. And if you look at the word analysis of variance, the analysis of variance short form is nothing but ANOVA, analysis of variance, which is used for more than two samples, or in case of F-test. The logical extension of F-test is ANOVA table or ANOVA analysis. So we always have to analyze the variance only in case of multiple samples, more than two samples. So that is the kind of summary of hypothesis testing method using T distributions, F distributions. So now we'll go to all these methods one by one and we'll see how to form the hypothesis test statement and then how to check them. So now we'll start with that process. Can you start now?
Yes, sir.
Okay, fine. So when I say hypothesis testing, it is a framework for decision making. Hypothesis testing is nothing but a framework for decision making. And when I say framework, we have certain process for decision making. So step number 1 says you have to state the null hypothesis first, which is H naught. Then state the alternate hypothesis, H1. Third step is you have to fix the confidence level. We'll discuss the confidence level concept also now. Fourth step is you have to either collect the data or you have to use the collected data. Generally, we get ready-made data. So fourth step is not required. You will get the required data. Step number 5 is then you have to use a specific statistical method. Whatever method we have discussed, either based on samples or based on what type of parameters you have to select appropriate statistical method, and then you have to come to conclusion whether to accept or reject that hypothesis. So this is a 6-step approach for making any decision in hypothesis testing, and you have to follow this 6 steps only. So now, when I say method, you have to use appropriate statistical method. For decision making, we have 4 different methods. For decision making, we have 4 different methods. First method is using confidence level intervals. Using confidence level intervals. And if you have looked into the regression output carefully, in the coefficient table, last 4 columns are about 95% confidence level. So that is the upper limit and lower limit of 95% confidence level. So the same thing now we are going to calculate in method number 1. What is the upper limit and what is the lower limit of 95%, 90% confidence levels. So that is one part of that regression table. Second method is using Z value, which actually we have already done in normal distribution, but we'll see how to use that to do the decision making. Third method is using T value. So we are going to look at all these T methods like 1 sample T test, 2 sample T test, paired sample, independent sample. So that is using T value. And the last method is using P value. That is P value analysis. So we'll discuss the P value analysis part also. And for more than 2 samples, another arrow will come as using F value. For more than 2 samples, you can say we have another method using F value. Using F value. That is ANOVA analysis. That we'll be doing in tomorrow's session. Okay. So these are the typical methods for hypothesis testing. Now in this case, if you look at the first method, we are trying to calculate an interval of values. We are trying to calculate a set of values. So this is called as interval method or interval estimation method. And remaining methods, we are discussing only one point. Z is a single value, T is a single value, P is a single value, F is a single value. So these are called as point estimation method. So we have one interval estimation method and we have 3 to 4 point estimation methods for decision making in hypothesis testing. So now what we'll do is we'll start this process. First, we'll again go back to the same example which we have discussed from day 1. I want to calculate average salary of IT professionals working in Hinjewadi Phase 1 Pune, suppose. So before starting the process, you must have some assumption that I believe that the population mean is 85,000. There is the population mean which is in some form of report, some financial report is there, last year report is there, which is mentioning that 85,000 is the average salary of IT professionals in Hinjewadi Pune. So based on that, my basic assumption is 85,000. The population mean is 85,000. Now this is important statement how to write the null hypothesis. How to write the null hypothesis. So what is the notation of null hypothesis? The notation of null hypothesis is H naught. This is pronounced as naught, H naught. Now because the notation says H naught, this is a hint to you. Because the notation says H naught, the hypothesis statement should have no not kind of word in the statement itself. The hypothesis statement should have the words like no and not in the statement itself. So when I say mu equal to 85K, that which is my basic assumption, how can I write my H naught? I can write H naught as there is no difference. No is important. There is no difference between average salary and 85K. There is no difference between average salary and 85. That means I'm accepting my assumption. I'm trying to accept my assumption. I want to accept my assumption as correct assumption. That becomes my H0, null hypothesis. If this is my null hypothesis, what will be my H1? That mu is not equal to 85K. Can we make above statement with 100% confidence? Whatever is my H0, can I make this claim with 100% confidence? Answer is no, because I don't have data with me. I have not done analysis. So we need to define the appropriate confidence level also. So at what percentage of confidence I am making this claim. And that confidence level, or you can say significance level, notation is alpha. And now I'll tell you how to define alpha also. Consider the default alpha for any kind of analysis, for any kind of tool. You can be using SPSS, SAS, any kind of tool. Always the default confidence is considered as 95%. So when I say 95% confidence, I am considering 5% of significance level. That is 0.05. So we'll go ahead with 95% confidence level for this problem. So I have gone ahead with step number 1, which we have discussed, that state the null hypothesis, alternate hypothesis, fix the value of alpha, collect the data. So I have done all those things. I have fixed, I have stated H0, H1. I have fixed the confidence level, 95%. Now I'll collect the data, and then I'll apply some statistical method or tool to conclude by accepting or rejecting the H0, or by accepting or rejecting the H1. So that is my process. So I will continue with this process. So we have all these things now in notation terms. This is my H0, this is my H1, this is my alpha. All these things are with me. So the data collection phase has to be started. As we have discussed, the complete population I cannot go ahead with. So I'll maybe select only 10 few companies and only few employees from those companies, maybe 10 employees per company. So I'll have a data set of 100 employees, for example, which is a sample for me. And I'm dealing with a sample of 100 employees, which are a representative of the total population. And then I'll apply some statistical method or tool. Suppose I'm using method number 1, which is the confidence interval method. And using this method, then I'll calculate these values, and then I will conclude whether to accept or reject. Now, how I will use method 1 and how I will conclude, that I will explain. Now, if you look at the formula for interval estimation, if you look at the formula says x bar plus or minus CL sigma upon root n. So x bar is the mean of the sample. So if you have data with you, you can easily calculate x bar. Plus or minus. So when I say plus or minus, then I'm trying to calculate two values, with plus one value, with minus one value. CL stands for confidence level constant. CL stands for confidence level constant. So I have given few confidence level constants to you, which are the like always used, like 95%, 90%, 99%. I'll also tell you how to calculate these constants. There is a method to calculate this constant, because tomorrow if you come across a problem where you have to find at the confidence level of 85% or 80%, then where to find the constants for those confidence levels. So I'll tell you how to find the constants also. That is my this term CL, confidence level constant, multiplied by this sigma, that is standard deviation. So again, if you have data with you, you can calculate standard deviation, and divided by root n. Root n is number of observations. So if you know number of observations, you can find root n also. In a way, if you look at this term sigma upon root n, actually this is standard error formula. Whatever standard error we have received in regression analysis, this sigma upon root n is standard error formula. And this standard error you can directly get in descriptive statistics. In data analysis, in descriptive statistics, we have seen standard error. That standard error is this value. So instead of calculating sigma and root n separately, you can directly substitute standard error value here. Fine. Now when I say x bar plus or minus, suppose my x bar is 10. And confidence level into this term comes as suppose 2. So I'm trying to calculate the interval of 10 plus or minus 2. Now we have, if suppose we have some x bar value as 10, and suppose some value which I have calculated with a CL value sigma and n, which comes as 2. So when I say 10 plus or minus 2, I'm creating a range of values. 10 minus 2 is 8 and 10 plus 2 is 12. So all the values between 8 and 12. So I'm creating an interval of values. In hypothesis testing, always remember, in hypothesis testing, we have to have a defined set of accept values and reject values. We have to have a defined set of accept values and reject values, and then we need to check our original claim, which is H0. My original claim, which is H0, is it part of my accept values or is it part of my reject values? If it is part of my accept values, then my assumption is correct. If that H0 is part of reject values, then my assumption is wrong. It is as simple as that. So in this case of confidence interval, what I am trying to create is I am trying to create a set of accept values. So this becomes set of my accept values. Then I need to check whether my H0 belongs to, this symbol is belongs to, whether H0 belongs to my set of accept values, then my assumption is correct or true. If H0 does not belong to my accept values, then my assumption is wrong. So H0 is wrong. So that is the process or method, and the same rule I have given here. The same rule is given here. If you look at the rule says because my H0 is 85K, because my H0 is 85K, if 85 belongs to the 95% confidence level, that means this value, this set, this interval, then we fail to reject H0. That means I want to go ahead with my assumption. So we say we fail to reject H0. So that is a rule, but we will solve examples using this method, and then you'll come to know more, you'll get more clarity about this. So we'll solve more examples, but right now this is a rule. So rule is like this: you have to check your H0 with your interval, confidence level interval. If H0 belongs to confidence level interval of accept values, then you go ahead with your H0. That means you fail to reject H0. That means you are going ahead with H0. Fine. Now we'll talk about confidence level. What is this confidence level? Now consider following examples. First scenario is I'm recruiting for Wipro. The previous batch I have taken for Wipro, so the same example I'm continuing. Recruiting for Wipro. And the second scenario is providing metal sheets to ISRO for some space program. So these are my two scenarios. In first scenario, my null hypothesis or my assumption is that candidates who are appearing for recruitment process, they know coding, because that is my basic requirement. So if they know coding, they can come and appear for the test, and then I'll select from the candidates. For the second scenario, my assumption is like the thickness of the metal sheet, because that is what I want. The thickness of metal sheet is 10 mm. It has to be 10 mm, which I'm using for some kind of device. Now in these two assumptions, if you look at the first assumption, recruiting for Wipro, where I'm expecting the candidates to know the coding part, even if one candidate writes, suppose I'm expecting some 100-line code from all the candidates, even if the candidate writes 5 to 6 lines of wrong code, even if the candidate writes 5 to 6 lines of wrong code, I may go ahead and I may select that candidate, because he has that candidate has written 95 lines very correctly. First thing, that also shows that he is good in logical thinking. He is good with syntax. There are minor mistakes which that candidate has done and which are okay with me. So I am okay to accept that 5 to 6% of error. In case of 100 lines, wrong code of 5 lines, that means even if a wrong code of 5 lines has been written by that candidate, I am still okay, and I'll go ahead and will select that candidate. So in that case, what I can say is I am okay to accept 5% of error or 5% of failure in my acceptance, in my candidate's acceptance. That is okay. But if you look at the second scenario, thickness of metal sheet is 10 mm, because it is related to ISRO space program, which is a very sensitive program. And in that case, even if the metal sheet, the thickness of the metal sheet is 10.00001, even that is not accepted. So even that much amount of deviation, that much amount of error is not accepted in second scenario. So what kind of error, what kind of chance of error you are ready to accept? You are ready to accept. That defines your confidence level. So my confidence level in first case, in first scenario, in case of recruiting Wipro can be 95%. Even if 90%, I can go ahead and I can select the candidate. But in second scenario, in case of ISRO program, I have to be 99.9999% sure. So that is the difference between level of confidence, and that is the meaning of confidence level. So what is confidence level? It is the capacity of accepting the claim with some error in it. The capacity of accepting the claim with some error in it, or I can say it is a risk appetite. It is the risk appetite, nothing else but a risk appetite. So that is called as level of confidence. And level of confidence is always related to the significance level. So if my confidence level is 95%, my significance level comes at 5%. If my confidence level is 90%, my significance level comes at 10%, and so on. So this is the basic meaning of confidence level. So it is dependent on the domain. What kind of domain you are dealing with. If you're dealing with scientific domain, if you're dealing with medical domain, your confidence level has to be on the higher side. But if you're dealing with political domain, like exit polls or something like that, then even if your confidence level is at 60%, 65%, that is accepted. So even if your claim is at 60% that some party will win in this election, that is okay, that can be accepted. So it is based on domain, what kind of confidence level you should have, and what kind of level of error you can take ahead in your calculation. Now we'll try to solve this problem. An engineer measured the hardness of 25 pieces of a ductile iron that were subcritically annealed, and the resulting data is given as follows. The engineer wants to verify that if the mean hardness of all such ductile iron pieces is 170. If it is 170, then only he will accept the consignment. Otherwise, he will not accept this consignment. So in this consignment, you can see there are 25 items, 1, 2, 3, 4, 5. Yes, we have 25 items. And average hardness the engineer is expecting is 170. The expectation from engineer is average hardness has to be 170. So what my H0 will be, my null hypothesis will be, the average hardness and 170 are not different. That means mu is equal to 170. Similarly, the H1 will become exactly opposite of H0. Mu is not equal to 170. Now, by default, we are going to check this problem at 95% confidence level. So alpha will remain as 0.05, which is the default value. So to calculate the interval values, what we need to calculate is X bar. Then we need to calculate the standard deviation and root n, or the standard error, combination of both of these. So my suggestion to you is I have given this data set in the Excel sheet, which I have shared in the morning. Don't use pen and paper. Directly use the Excel sheet. Go for descriptive statistics. You will get the mean value. You will get the standard error value. Just put those values and calculate the interval values, which is the accept range for this problem at 95%. So now, first of all, you need to run the descriptive statistics to get all the values. So I'll go to data analysis, descriptive statistics, input range. This is my input range. I'll select all the values, and output, suppose I want to display my output at this location, and I want summary statistics. I'll click on OK. So it is giving me all the values what I want. Mean is 172.52. That is part of my formula, and standard error is 2.06. So what I want to calculate is 172.52, or I can directly use this cell. Now plus or minus. The formula says plus or minus. So first I'll go for plus. What is the confidence level constant for 95%? I have given the table. So what was the confidence level constant for 95%? Yes. It was 1.96. It was 1.96. So remember those constants carefully. So I'll say 1.96 into the standard error. Standard error is this. So that is my upper value of my confidence interval. Similarly, I have to calculate mean minus 1.96, which is the constant, into standard error. So this becomes my interval, 168.47 to 176.56. This becomes my confidence interval of 95%. Have you got the same values? Are you getting the same answers?
Yes, sir.
So only change is I have changed the confidence level constant from 1.96 to 1.65 to 2.57. That is the only change. And these are the intervals which I am receiving for 95%, 90% and 99%, correct? So now we'll shift back to the presentation now. What my null hypothesis is, mu is equal to 170. So I'll check whether 170 belongs to my accept range of values. So 170 belongs to accept range of values. That means my assumption is correct. I can go ahead with H0. My assumption is correct and I can go ahead with H0. Once I say I can go ahead with H0, that means we say we fail to reject H0. In analysis terms, we say we fail to reject H0. Can I say the same thing at all confidence levels? Even at 90%, you look at the interval. 170 belongs to this interval also. 170 belongs to second interval also. And 170 belongs to third interval also. So at all confidence levels, 90%, 95%, 99%, at all confidence level, we say that 170 belongs to the accept range of values. That means we can go ahead with H0. My assumption is correct. We say we fail to reject H0 at all mentioned level of confidence. We fail to reject H0 at all mentioned level of confidence. Have you understood this? Can we go ahead?
Yes, sir.
Okay. So now try to solve this problem. Data is given to you in Excel already. From the problem, you can come to know that my H0 will be mu is equal to 15.7. Mu is equal to 15.7. That is my H0. N is given to you 33. Use the constants, use the formula, and tell me the accept range for all confidence levels and whether to accept or reject my H0. When I say H0 is my mu is equal to 15.7, I'll check whether 15.7 is part of my intervals or not. So I can say 15.7 is not part of 90% interval also. It is not part of 95% interval also, and is not part of 99% interval also. So I can say my basic assumption is wrong. My H0 is not correct. And we reject H0. At all mentioned level of confidence, we say we reject H0. My basic assumption is not correct. So what was the basic assumption? That the standard height is 15.7. So my basic assumption is wrong. We reject H0. So standard height is not 15.7. It is something else than 15.7. So that is my conclusion. Now the important part is, because I have given you the confidence level constants for 90%, 95% and 99%, and which comes to be something like this 1.65 for 90%, 1.96 for 95%, and 2.57 for 99%. But what if I tell you to calculate the confidence at confidence level of 80%? So how to find constant for 80%? So I'll tell you the method to find constants for these confidence levels, and for that we need Z table. So Z table I have already shared with you in yesterday's session. So please open the Z table.
Yes, sir.
Yes, okay. Now I have also shared the constant values on the WhatsApp group for your reference. What is 90%, 95%, 99% confidence level constants? So what is the constant for 90%? 1.65?
1.65.
Correct. Now when I say confidence level of 90%, when I say 90%, that is 0.9. When I say 90%, that is 0.9. And because in case of Z table, we always look at one side of the mean, we always consider half of the confidence, that is 0.45. So look at the closest value to 0.45 in this table. Look at the closest value to 0.45, 0.45. So I can say this value or this value, maybe this value. This is the closest value to 0.45, correct? So what is the Z value of this 0.45? Just please tell me what is the Z value of this 0.45?
1.65.
Correct. And that is the constant for 90%. Getting it? Now we'll check for 95% also. What is the constant for 95%? 1.96, correct? So what is the half of 95? First of all, 95%. What is meaning of 95%? 0.95. What is the half of 0.95? What is the half of 0.95?
0.475.
0.475. Look at for 0.475. We have the exact value, 0.475. What is the Z value of 0.475? 1.96?
Yes, sir.
And that is the constant for 95%. Just check whether this is correct for 99% also. What is the constant for 99%? 2.57, correct? 2.57. So what is 99% means 0.99. What is the half of 0.99? What is the half of 0.99? 0.49 something?
0.495.
Correct. Which is the closest value? 0.495. Maybe this or this. Either of this. What is the Z value of this? 0.4949. 2.57. That is a constant. So can you calculate the any confidence level constant now for the calculation purpose?
Yes, sir.
So can you tell me the confidence level constant for 80%? %80 is 0.8, half of that is 0.4, the closest value is this 0.399. And the Z value for this is 1.28. So that becomes my constant.